Now in this video, I want to start on some ideas that would eventually lead on to the phenomenon of tunneling. So instead of looking at electrons, let me start by looking at something quite normal. Right, let's say I have, let's say that's the ground, and this is a slope. Okay, this slope might be a road going up or just a hill slope. Now suppose that I have a little, suppose I have a little ball, here, which I set off, or which I kicked off with velocity v. Okay, velocity v. So this ball takes off, assuming that the ground is quite frictionless. This ball takes off with a kinetic energy of half mv squared. Where v is the velocity and m the mass of the ball. So as the ball reaches the slope, it starts to go up, and as it goes up, it has to do work against gravity, so it gains in potential energy mgh. Okay, and this work comes from the kinetic energy, so kinetic energy decreases. In other words, the ball slows down, and eventually, at some point, at some height, it must have used up all of its kinetic energy, and then it stops, and then it starts falling back down again. So this is the height where the potential energy is equal to its kinetic energy. So this is how we would understand it from classical physics, from Newton's physics. It goes up there and comes down. Now, and of course, we understand this, and of course the ball will not go up any further. Right? Absolutely not. It has used up all its energy. Right? There's no way it can go any higher. So it has to come back down once its kinetic energy drops to zero. Okay, so no problem. Now let us now take this idea and go into our hydrogen atom. Let's look at the picture of our hydrogen atom. Now we have, let's see, hydrogen atom, there's a proton at the center, plus P, okay, and there is an electron going around it, electron of energy E, of charge E. It's an electron there. So that's our usual picture of the hydrogen atom, or at least a simple picture. But now that we know electrons behave as waves, there would be a wave around the atom, and that's a bit more complicated. So I don't think I'll go into the wave details in the atom of the electron orbit in the atom, but I'm just going to take this idea of the atom and see how we can develop this idea of tunneling. So what I want to do is I want to use this idea of going up a hill. Now, what I'll do is this. Let me think about the potential energy of the due to the potential energy of the electron due to attraction by the nucleus. Now that is not unlike this hill slope. So let me draw a graph. So the vertical axis is the potential energy of the electron. Horizontal axis is just the distance. I'll call this x. Or I'll call it r. Okay, that's just r. And we know the relation, the equation for the electron's potential energy is just the Coulomb potential energy. U equals to minus Okay, we have E squared, because it's charge of this times charge of the electron times the charge of the proton, and it's minus because one of them is, because they have opposite charges, so we have a minus sign there. They're attractive. And we have 4 pi epsilon naught for the Coulomb's formula, and we have R. So that is the potential energy of the electron. Now if I plot a graph, this formula, the graph would look like this. Look like this. So in the hydrogen, suppose that the electron, now I'm not going to imagine an electron going purely in the circular orbit anymore. I'm just going to say, right, I have this proton here at the origin, okay, and I have an electron at some distance from the nucleus, and let's say the electron is moving, has a velocity that and is moving outwards. Okay, let's forget about the orbit for now. Let's have an electron moving outwards. Now if I have an electron here, now what I'm going to do is I'm going to think in terms of the kinetic and the potential energy. So we're going to have a, let's see, we're going to have a half an energy equals to Ke plus Pe. Okay. Ke plus Pe. Now the Ke is half mv squared plus the P is the U, which is negative as we see. And normally, if the electron is in hydrogen atom, it would the total energy would have to be negative. Okay, otherwise the electron would escape. Negative meaning that the kinetic energy is smaller in magnitude than the potential energy. So that since U is negative, the sum is negative. Right? If the kinetic energy is bigger in magnitude than the potential energy, then there would be enough energy for it to escape. So the total is normally negative. So suppose it has such a value, right? Suppose E has this value. It's a negative value, and suppose that the electron is here. That's the position of the electron. So if I just draw a little circle here to represent the electron, then at this position we know that the potential energy is here. It's given by this value here of U, and since the total energy is E, then that means that this amount here must be the kinetic energy. Okay, that's my U. So U, which is a negative value, is U. So U plus this amount, that's half mv squared, would be the E, which is this. Right, so that's the draw that. This is half mv squared. So you see, U plus half mv squared is E. So it all fits in together. Now let's say this electron starts moving in this direction. Okay, I've just drawn the electron here, but you might imagine that it's actually like my ball rolling up the hill. So as the electron moves from there to there, its potential energy increases, just like when the ball moves up the hill. So as the electron moves away from the nucleus, from the proton, its potential energy increases. So that's like my hill. Okay, so it's like the electron rolling up the hill. So as the electron moves further and further, okay, its potential energy increases because it has to do work against the attraction from the proton. And therefore, as it moves further away from the proton, which is here at 0, it must decrease in kinetic energy because the kinetic energy has to be used to do work against the attraction, so that its potential energy can increase. So when it reached this point here, the kinetic energy must become zero. Must be when the Ke becomes zero. Just like, here, when the ball rolls up the hill, at some point its kinetic energy is used up. Okay, so at some point the kinetic energy of the electron will be used up as it moves further away. So imagine that the electron is moving as a velocity in that direction. So I'm not talking about electron going around orbit anymore. I'm imagining that an electron is moving outward with a certain speed, v initially, and that v decreases as kinetic energy is used up. So at some point when the kinetic energy is completely used up, what happens then? It must stop and turn back, just like my ball would stop and roll back down. That's what we might expect from our so-called classical picture or Newton's picture. Okay, so maybe that's what will happen. But now let me look at this from the point of a wave. Let me look at this as a wave. How should I do this? Okay, maybe I should use let me use a dark blue color. Okay, for the wave, right? So when the electron is here, it's a wave, right? So it's a wave, goes up and down like a wave. Now, as it moves away from the nucleus, we know that the kinetic energy and therefore the velocity decreases, the momentum decreases. So as the momentum decreases, the wavelength gets longer. In the other direction, if it moves in the other direction, it must get faster and faster. Since it accelerates, it gets attracted and accelerates towards the nucleus. So we would expect that that the momentum increases and therefore the wavelength gets shorter and shorter. Right? We know this from the Broglie's relation, that wavelength is equal to h over p. Bigger the momentum, smaller the wavelength. So as I move out, momentum decreases because Ke gets used up against the attraction. So the wavelength gets longer and longer. And at this point, as I said, at some point, let's say this point, the Ke is completely used up. So what happens to the wave? That's the question. What happens to the wave down here? If the Ke gets completely used up and we expect that the electron just can't go beyond that, then the wave must drop to zero. No wave beyond that. That seems reasonable enough. Just like the ball cannot go any further when it used up its energy. So there must be no more wave beyond this point where the kinetic energy has dropped to zero. Now, but notice that we have a very strange, very unusual wave here. We have a wave that just got cut off. We have a very sharp and sudden drop in the wave to zero down here. So, what does this mean? Now, actually, this means that there's a lot of energy, because if I have a very sharp and sudden change in the wave, it's like a wave that is oscillating very rapidly. Now, if you take a wave that's oscillating very rapidly, it means that this wave has a very short wavelength. It's a very short wavelength. Okay, and you know P equals to h over lambda, right? The Broglie's relation. If it has a very short wavelength, it has a very big momentum and therefore a very big energy. So if the wave drops suddenly to zero, it's as if at this part where it drops suddenly to zero, it's like part of a wave which is oscillating extremely rapidly. Okay, so it means that at this point, this very sharp drop, a lot of energy is involved. And that can't be right because it's like a lot of energy is suddenly being created down there. Okay, so that can't be right. So if that can't be right, what really happens? What actually happens then? What happens is that it must remain smooth beyond this place where the kinetic energy is used up. The wave must remain smooth, right? It's forced to remain smooth because otherwise, if it drops suddenly, a lot of energy is involved. But we also know that since the kinetic energy is already used up, it is really not possible to have any electron beyond this point. So even if there's a wave, even if there's this wave slowly coming down here, it has to keep getting smaller and smaller until it's eventually almost zero, right? Surely, even if there's some wave there, we must expect that much further away there should be no wave. The electron can't possibly be wandered so far away from the point where its kinetic energy has already dropped to zero. It's like imagining that my ball would just keep wandering up the hill after it has used up all its Ke. So surely there must be no electron further away. But at this place where it's still quite close to the part where Ke has been used up, the fact that energy must be conserved, right, means that it forces, combined with the fact that the electron behave as a wave, right? This means that there must be some wave, there must be actually some amplitude of the wave, some amount of wave beyond this point where the Ke has been used up. Now this is a very strange situation. It's a bit like saying that my ball, which has rolled up the hill and to a height where it has used up all its kinetic energy, all right, to the point where I expect my ball to stop and come back down. It's a bit like saying that there's still some chance of finding my ball a bit further up beyond that. That is very, very hard to imagine when we are actually rolling a ball and looking at it. Okay, it's very hard to imagine that once it has used up all its Ke, there's still a chance that we can find it a bit further on. But that's exactly the kind of thing that we're talking about here when we talk about the wave property of the electron. At the point where it has used up all its Ke, there's still a chance of finding it at some distance beyond. Okay, because that is forced to happen by the fact that it's a wave, because otherwise, if it stops completely there and there's no wave, then the very sharp drop in this wave, this so-called wave function, must mean that a lot of energy is involved, because it's like an extremely short wavelength wave at this region. Now, this likelihood of finding the particle beyond this place where the kinetic energy has been used up has a name. It is called tunneling. And we might imagine that this name comes about because the only way we might expect to be able to find my ball a bit further beyond this place where it has used up all its Ke is if we dig a tunnel through the hill. So it's kind of just a picture, just a way to picture the situation. So it's as if I think about this as a hill or some kind of a barrier. In fact, that's how it's normally called, a potential barrier. It's as if the electron digs a hole and tunnels through this potential barrier.